Hey there! Welcome to Lab Partner 101, your study buddy for making science and math simple. I'll walk you through tough concepts step by step so you never feel lost. Let's dive in. If you find value in breaking down science and math step by step, make sure to subscribe to Lab Partner 101. That way, when we tackle concepts like motion, forces, or even black holes, you'll be right there with us. Now, let's get into Newton's laws of motion. Today we're unpacking Newton's laws of motion. 3 deceptively simple statements that explain nearly every physical interaction in our daily lives. They cover why seatbelts save lives, how rockets can fly in the vacuum of space, and why it's harder to push a heavy couch than an empty shopping cart. Isaac Newton was born in 1642, just months after Galileo died, almost as if one giant of science handed the torch to the next. He grew up in England during a time when many believed that the heavens followed mysterious, perfect rules, while the earth down here was messy and unpredictable. Newton would come to change that misconception forever. He wasn't just a physicist, he was also a mathematician, astronomer, and even dabbled in alchemy and philosophy. But in 1687 he published his greatest work, the Philosophiae Naturalis Principia Mathematica, usually just called the Principia. In it, Newton did something radical. He showed that the same physical laws govern both the fall of an apple from a tree and the orbit of the moon around the Earth. That was shocking at the time. Before Newton, most people thought earthly motion and celestial motion were governed by completely different rules. Apples dropped straight down, while planets and moons circled gracefully overhead. Newton revealed that they were not separate phenomena at all, but part of one grand system described by the same mathematics. Think about the power of that leap. It meant that the universe was understandable, predictable, and connected. With just a few clear principles, Newton unified the motions of falling objects, cannonballs, tides, and planets. His laws of motion weren't just theories about everyday life. They were a new framework for science itself, laying the foundation for modern physics and engineering. Newton's first law is often called the Law of Inertia. In plain English, it says this: an object at rest will stay at rest, and an object in motion will keep moving at the same speed in a straight line, unless acted upon by a net external force. That word inertia is important. It means resistance to change. Objects don't start moving, stop moving, or change direction by themselves. Something, a push, a pull, friction, or gravity, has to cause that change. We can also express Newton's first law in equation form: sigma F equals 0, then A equals 0. Read out loud, that means the sum of all forces acting on an object equals 0, which implies the object's acceleration is 0. Let's break it down. The Greek letter sigma, followed by F, means the sum of all the forces acting on the object. That includes gravity, friction, normal force, tension, and so on. Equals 0 means those forces cancel out. There's no leftover or unbalanced force pushing harder in one direction than the other. A equals 0 means the acceleration, written as A is 0. In other words, the object's motion isn't changing. Now here's the subtle but crucial part. 0 acceleration doesn't mean 0 motion. It just means the motion stays constant. If the object was sitting still, it stays still. If it was already moving, it keeps moving in a straight line at the same speed. Let's take a simple example. A book resting on a table. Gravity pulls the book downward with a force. That's its weight. The table pushes upward with an equal force, called the normal force. When you add them up, they cancel. Sigma F equals the force of gravity plus the normal force equals 0. Spoken out, the sum of forces equals the downward gravitational force plus the upward normal force, and that total is 0. Since the net force is 0, the acceleration is also 0. The book just stays at rest. Now imagine you give the book a shove. At first it moves, but then it slows down and stops. Why? Because friction is acting opposite the motion. That friction is an unbalanced force, so the velocity changes until the book halts. But if the table were perfectly frictionless, no resistance at all, the book would slide forever at the same speed, never stopping. That's inertia in action. In our everyday world, we almost always see objects slow down. That's not because Newton's law is wrong. It's because friction and air resistance are everywhere. Remove those forces, and you see the first law clearly. That's why astronauts on the International Space Station can float a tool across the cabin, and it just keeps going in a straight line until it hits something. Suppose you slide a hockey puck on perfectly frictionless ice at 5 meters per second. No one touches it. How fast is it going 10 seconds later? The answer: it's still moving at 5 meters per second. Why? because sigma F equals 0, which means acceleration is 0. No acceleration means no change in speed or direction. The puck just glides. That's inertia. Newton's second law is really the engine of mechanics. It connects force, mass, and acceleration in a single powerful equation. The law says this: the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. In symbols, it's written as sigma F equals m times a. Read aloud, the sum of the forces equals mass times acceleration. Here's what each piece means. Sigma F means the net force, the total of all the forces acting on an object, after adding them together with their directions. M is the mass of the object, measured in kilograms. Mass is a measure of inertia, how much an object resists a change in its motion. A is acceleration, measured in meters per second squared. Acceleration means a change in velocity, either speeding up, slowing down, or changing direction. This equation tells us two things at once. Push harder, apply more force, and you get more acceleration. Increase the mass, and acceleration drops for the same force. It's why you can shove a soccer ball easily, but struggle to push a stalled car. The mass difference is everything. That's also why an athlete training with a light sled can sprint quickly, but add heavy weights to the sled, and acceleration slows dramatically. The same legs, the same push, but the extra mass reduces the result. Let's solve a simple case. Suppose a student pushes a 10-kilogram box with a force of 50 newtons. Ignoring friction for now, what's the acceleration? We start with the equation F equals m times a. Solving for acceleration, a equals F plus m. That's 50 divided by 10, which gives 5 meters per second squared. That means the box's speed increases by 5 meters per second every second the force is applied. In just 3 seconds, it would be moving at 15 meters per second if the push continued. Now let's make it realistic. Suppose friction pushes back with 20 newtons in the opposite direction. The net force is 50 minus 20, or 30 newtons. So A equals F plus m equals 30 divided by 10, which equals 3 meters per second squared. Notice what happened. Friction reduced the acceleration, but it didn't eliminate it. The box still speeds up, just not as quickly. Newton's second law isn't just for boxes on a floor, it explains rockets leaving Earth. For a rocket to lift off, the thrust has to exceed its weight. Weight is mass times the force of gravity. Suppose a rocket has a mass of 2 million kilograms. Gravity pulls down with 2 million times 9.8 newtons, about 19.6 million newtons. Now imagine its engines produce 35 million newtons of thrust. The net force upward is thrust minus weight, 35 million minus 19.6 million, or 15.4 million newtons. Divide that net force by the rocket's mass, 15.4 million divided by 2 million. That gives an upward acceleration of about 7.5 meters per second squared. In other words, every second the rocket's speed increases by another 7.5 meters per second. That's how it escapes Earth's grip. Newton's second law gives us a direct link between the invisible pushes and pulls around us and the visible changes in motion we see every day. From shopping carts and sleds to satellites and spacecraft, this law is the reason we can calculate, design, and predict motion with such precision. Newton's third law is probably the most quoted of the three. For every action, there is an equal and opposite reaction. But what does that mean exactly? What it really means is this: forces always come in pairs, and those pairs act on different objects. If object A pushes on object B, then object B pushes back on object A with the exact same force, but in the opposite direction. Take a rocket launch. The rocket engines blast gases downward at tremendous speed. That's the action force. The gases, in turn, push the rocket upward with equal force. That's the reaction force. The two forces don't cancel, because one acts on the gas and the other on the rocket. The result? The rocket lifts off. You see the same principle every time you take a step. Your foot pushes backward on the ground. The ground pushes forward on you with equal force. It's that reaction force from the ground that actually propels you forward. Without it, say on ice or in space, walking the same way wouldn't work. Imagine two skaters on frictionless ice. One skater pushes the other with a force of 100 newtons. By Newton's third law, the second skater pushes back on the first with an equal force of 100 newtons in the opposite direction. But here's the key: their accelerations aren't the same. If the first skater has half the mass of the second, they'll accelerate twice as quickly, because acceleration depends on both force and mass. The forces are equal, but the results aren't identical. This law also explains what happens during a spacewalk. If an astronaut pushes against the spacecraft pushes back. Both start drifting apart in opposite directions. The forces are perfectly equal, but the spacecraft barely moves, while the astronaut drifts quickly because their masses are so different. That's the beauty of Newton's third law. It's not just about balance, it's about interaction. Forces always occur in pairs, and those pairs shape every motion we see, from walking on Earth to launching rockets into space. With just 3 simple laws, Newton gave us the foundation of physics, rules so powerful that they still govern how we design, build, and explore centuries later. Engineers rely on these laws every day: the strength of a bridge, the safety of a car's crumple zones, the flight path of an airplane, and the controlled thrust of a rocket. All of them are calculated using Newton's principles. Without them, modern engineering wouldn't exist. Athletes live them out in every move. A sprinter pushes against the track to explode forward. A quarterback throws a football, relying on inertia and acceleration to carry it downfield. A gymnast's flips and landings can all be explained through Newton's framework. Even in entertainment, Newton's laws quietly shape our world. Video game developers program physics engines that mimic real motion: rolling balls, colliding cars, exploding rockets, all based on equations that come directly from Newton. Without them, digital worlds would feel fake and unconvincing. And beyond Earth, these laws are essential to space exploration. They explain how satellites stay in orbit, how astronauts dock spacecraft, and how probes can slingshot around planets on their way to the outer solar system. Every mission, from the Apollo moon landings to the Mars rovers, rests on the same 3 principles Newton wrote down in the 1600s. The impact of Newton's laws is everywhere. They don't just describe motion, they unlock the ability to predict and control it. They bridge the gap between theory and the real world, turning simple ideas into the foundation of technology, sports, safety, and exploration. If this breakdown of Newton's laws helped you, hit like, subscribe, and share Lab Partner 101 with a friend. And drop a comment with the kinds of problems or topics you'd like me to cover next. Your feedback drives this channel. Newton's 3 laws may be centuries old, but they remain the keys to unlocking everything from a sliding puck to a rocket ship leaving Earth. Next time, we'll push deeper into forces and energy, connecting these laws to the work, power, and conservation principles that run the universe.